Hello, my name is Mark, and I'll be speaking about isolation branching, a branch and bound algorithm for the K-terminal cut problem. First things first, what is the K-terminal cut problem? It's also known as the multi-terminal cut problem, and in the problem, we are given as input a graph G with vertices V and edges E. The graph is undirected and has edge weights Eij. The terminals are a set of K nodes in the graph. As output, we would like to partition the set of vertices such that each terminal is in exactly one set in the partition. We'd like to do this in a way that minimizes the total weight of edges that go between sets in the partition. Now, I've written the objective in a way that's slightly different. In the objective I've written here, we sum over each set and we look at the weight of edges that are leaving that set. When we do that, we end up double counting each edge that's between partitions because it leaves one set, it leaves the other set. And then we put a 1/2 there to account for that double counting. And we'll see why we formulated the objective this way later. Let me give an example. In this example, we have a graph with 4 terminals. Looking at this graph, there is a feasible cut where we remove 3 of the edges that have weight 3. If we were to do that, we would separate all the terminals from each other, and the resulting sets that remain connected to the terminals would be the partition. But that's only a cut of weight 9. A better solution is to cut all of the center square. If we do that, we have a cut of weight 8, and the resulting partition is as follows. There's been a lot of previous work to study the K-terminal cut problem. It's known that the problem is NP-hard. And so the approaches to this problem are either to find fast algorithms which are approximate, or to find not polynomial time algorithms which are exact. And so I've chosen to call those heuristic, the algorithms which are polynomial but not exact, and optimal, which are algorithms which are exact. And I distinguish between algorithms which are only described in theory versus algorithms which have actually been implemented. So the 2 approximation, which appeared in the same paper as the one which showed the problem was NP-hard, is easy to implement. Since then, there have been improved approximation factors, but they have not been implemented in practice. Finally, there are theoretical results which show that the problem is fixed parameter tractable with respect to the size of the optimal solution, meaning that if the optimal solution is fixed, then the problem is polynomial, but it's not polynomial in general. These algorithms are quite complex and have not been implemented in practice. So our goal is to fill in what we believe is the missing link here, and to find an algorithm which is both practical enough that can be implemented and returns the optimal solution. Granted, it won't be polynomial time. So our key contribution here is a practical algorithm. It solves the problem in seconds when the number of edges is less than about 100,000. And our algorithms, and when we analyze its running time, we'll see that it is fixed parameter tractable. And therefore, this is an alternative proof that the K-terminal cut problem is fixed parameter tractable with respect to the size of the optimal solution. So we need a few building blocks in order to explain how our algorithm works. The first is the idea of seed sets. A set of seed sets is a collection of subsets of the vertices such that each subset of the vertices contains exactly one terminal and they are disjoint. In a sense, this is almost a partition. The only property it's missing is that it does not necessarily include all of the nodes. So you can think of it as coloring some of the nodes, but not all of them. For example, this is a set of seed sets. The nodes colored yellow, nodes colored blue, nodes colored green, nodes colored red form each an individual seed set, so this is a collection of seed sets. This is not a partition because one of the nodes is not colored. This is also a set of seed sets. The next property that we need is the containment property. A set of seed sets has the containment property if there is an optimal cut such that the seed sets are a subset of the optimal cut. So the seed sets are subsets of the optimal partition. This coloring, this set of seed sets does not have the containment property because there is a node colored red that should be colored yellow. However, this set of seed sets does have the containment property because every node that is colored as it should be for the optimal cut. There are some nodes that are not colored, but that's fine. Finally, there's the idea of a minimum isolating cut. A minimum isolating cut for a seed set is a minimum cut that separates it from all the other seed sets. If we wanted to take a minimum isolating cut for the second seed set here, for the red seed set, we would have to cut the edge of length 3, the edge of length 2, and another edge of length 2 for a total cut size of 7. However, if we wanted to compute the minimum isolating cut for, say, the fourth seed set, the green seed set, we would only need to cut 2 edges for a total cut weight of 4. In this example now, if we want to isolate the red vertices, the red seed set, we only need to cut 2 nodes again, 2 edges again, both of weight 2. If we want to do the minimum isolating cut for set T1, or for the first seed set, the yellow seed set, we can do that by just cutting 1 edge of weight 3, and that gives us the minimum isolating cut of weight 3. With all of these building blocks, there's one key lemma that we need in order to describe our algorithm. That is the seed set isolation lemma. But first, a little bit of notation. Let's say we have a seed set Si, which is in a collection of seed sets, and we take the isolating cut. When we do that, we've separated Si from the rest of the graph. Now, the nodes that remain connected to Si, those are what we're going to call the source set of the isolating cut. And we use I of S to make that to denote that. Now we can state the key lemma. If we have a collection of seed sets with the containment property, and we take the isolating cut, we isolate one of them from the rest of the vertices, from the rest of the seed sets, then the vertices which stay connected to Si are necessarily going to stay connected to Si in the optimal solution. Or in other words, the containment property continues to hold. So how are we going to use this in our algorithm? Well, what we're going to do is we're going to start with the smallest possible seed sets, which are just the sets that each set containing a terminal. And we're going to, as much as possible, use isolating cuts to grow these sets. And when that's no longer possible, when the isolating cuts don't give us any more information, they're not adding any new vertices to these sets, then and only then will we branch. And when we branch, it just means that we're going to take a vertex, which is not assigned to any of the seed sets, and we're going to try assigning it to each of the seed sets. And once we've done that, we're going to continue in each of those new nodes in the branch and bound tree. We're going to continue using isolating cuts as much as possible, then branch all the way until we hit a leaf node. Now, if that was a little bit hard to follow, I think this picture will clarify everything. Let's say that we have the seed sets S1, S2, S3, and a vertex which is not in any of S1, S2, S3. If possible, we would like to take an isolating cut to grow S1, S2, or S3. But let's say that we get to the point where the isolating cuts don't add any new vertices. If we take the isolating cut for S1, we just get S1 back. At that point, what we're going to do is we're going to try to take V, and we're going to try putting it into S1 and continuing to take isolating cuts. We're going to put it into S2 and continue taking isolating cuts, and put it into S3 and continue taking isolating cuts. And here's the key idea. Because S1, S2, S3 have the containment property, in at least one of these new branch and bound nodes, we must have added V to the correct source set. And that means that before we took the isolating cut, at least one of these children nodes had the containment property. And that means that when we took the isolating cut by the seed set isolation lemma, we also preserved that property. And we call this inheritance. Because we started off with a node that had the containment property, at least one of its children nodes has to have the containment property. For example, in this case, it could be that the containment property went down from the parent node to the node where we added it to source set 3. So all of this comes together to show that we have a correct enumeration strategy, which means that if we start from our top node and we go down the branch and bound tree, eventually there will be a leaf node that has the containment property. And if it's a leaf node with the containment property, that means all the vertices are assigned, which means that we have a partition, which means we have an optimal K-terminal cut. But enumerating is not necessarily a good idea. So we need to bound. To establish a bound, we're going to return to the objective function. Recall that the objective function measured the total weight of edges between the different source sets. But we chose to write it in the way where we were measuring half the total weight of edges leaving each source set. This allows us to generalize pretty nicely to the case where we have seed sets instead of source sets. So we're not partitioning everything. In this case, we're still going to take half the total weight of edges that are leaving each seed set. When we do this, it's clear that this value at a leaf node is the value of a feasible K-terminal cut. And further, one can show the useful lemma that this value increases when you go from a parent node to a child node. As a consequence, if we always consider the node with the lowest value of this objective, then the first leaf node that we ever hit will be the leaf node with the optimal objective value. Furthermore, if at any point we have a feasible solution, we can ignore any node in the branch and bound tree whose value of this objective is larger than that feasible solution. Because we know that continuing the branch and bound algorithm from that node is never going to give us something better. It's always going to get worse. This value is always going to increase. So that concludes the explanation of how the K-terminal cut algorithm works, the isolation branching algorithm. If you'd like to give it a shot, you can find it on GitHub. you can see that it only takes a few lines of code to get started.